It's a great pleasure to have Alexandre as a seminar speaker today. So, just for a brief introduction, he is a lecturer at University of Saint Etienne of France and also part of LMFA of Lyon. He works on various topics of turbulence, convective instabilities in porous media, blood flow, rotating turbulence, stratified effects, and so on. In fact, I happened to be an online meeting of his PhD student, and that's where we got to see his interesting work. And then I invited him, and it's very exciting work by him and his group. So we like to hear his research topic now. So Alexandre, please take over the Zoom session now.
So thank you, Mahendra. Thank you for to invited me. And so, okay, I will start. So today I will talk about interaction between wave, eddies, and large structure in rotating or stratified turbulence. This is the main result of the PhD of Henri Lame. We work together, me, Alexandre, and Fabien Godfer with Henri. But the main result comes from Henri. We have a collaborator for the group is Andrea Maffioli. He works on the same laboratory as us, and it is in Lyon. In Lyon, it is in France, in fact. Okay. So this is the topic, the summarize of my topic. Okay, we have an introduction. I present you a new separation technique to extract the wave and eddies in the flow. And after, I can use this separation technique to interpret and to obtain the interaction between wave eddy in stratified turbulence and in rotating turbulence. And we treat about some physical phenomena, two different physical phenomena in stratified and rotating turbulence. And finally, I present the conclusion. Okay. So first, the motivation of wave. In the atmosphere or in the ocean, in particular in the ocean, we find the internal gravity wave. The internal gravity wave is due to the gravity of the atmosphere. And for example, the gravity of the atmosphere. And for example, on the right picture, you can see on the troposphere the gravity waves that occur in a cloud. Okay, like this. The gravity wave occur in the ocean, and it is responsible to the mixing in the interior of the ocean. It is responsible to the transport of heat, and nutrients, and it dissolves the greenhouse gases. In the atmosphere, the internal gravity wave occur in the middle of the atmosphere and mixed air and are mixed with some eddies. The other point is that it is demonstrated that in 25 years ago that the quasi-biennial oscillation is a jet close to the equator, and his oscillation and his creation is mainly due to the interaction of internal gravity waves that form the quasi-biennial oscillation. And this quasi-biennial oscillation is like it's a very periodic phenomena in weather and in climate. Excuse me. So okay, this is the effect of the internal gravity wave on ocean and on atmosphere. But we have also inertial waves. The inertial wave depend on the rotation of the Earth. And for example, on the right picture, you can see that the jet stream is deformed by the Rossby wave. The Rossby wave is a kind of inertial wave. The inertial wave impacts the large scale, mainly the large scale, in particular the large scale circulation. So it impacts the large scale of ocean and impacts the jet stream, as I say. But you can find internal gravity wave in the turbo machinery. It's not huge, but you can find this, and you can improve the efficiency by play with inertial wave or the stability of your turbo machinery. So far from the wall, in the interior of the ocean or in the interior of in the core of the atmosphere, we can do an hypothesis of homogeneity. We can use the homogeneity, and we have the homogeneous stratified turbulence, which is a mix between the classical turbulence with ADs and some internal gravity waves. This occur in the stable stratification. This means that the heavy part it at the bottom and the lighter part it at the top. So we have the dispersion relation for this wave. K is the wave vector. We have oscillation around in the direction of the wave vector. And the frequency of the wave vector is linked not to the wave vector k, but with the angle of the wave vector, theta. And this angle is the angle with the horizontal plane. So we have a coefficient between the frequency and the angle and the cosine of the angle of the wave vector. And this coefficient is the Brent-Vassiliev frequency. It is linked to the mean gradient. It is linked to the gradient, the mean stable gradient, in fact. So we can produce some stratified turbulence. And as you can see, this is a typical picture in DNS that is obtained by Andrea Maffioli. We have, in fact, some large structure. We have maybe some overturning of the density, but we have also a large structure that vary mainly vertically. This large structure are called shear mode. Note that the dispersion relation is independent of the modulus, and we have classically the internal gravity wave occur at large scale until the Osmedov scale. I come back on this definition after. But we have a range of large scale that is where the integral gravity waves occur. For the rotating turbulence, we can do an hypothesis of homogeneity. We are far from the wall. So we have the classical turbulence with ADs and etc. And we submit this turbulence to the rotation with omega, the rotation rate. So we have now the inertial wave. This inertial wave have a different dispersion relation is linked to the sinus of the theta. Theta again is the angle with the wave vector and horizontal plane. So we have cosine for internal gravity wave and sine for the inertial wave. For the rotating turbulence, the large scale is different. It's more like a big column. In fact, it is a geostrophic mode in that more or less don't vary along the vertical axis. And it is an equilibrium, a balance between Coriolis force and horizontal pressure. It is compatible with Taylor-Prodman, okay? It's a linear theorem. And this inertial wave occur at the large scale, from the biggest large scale to the Zeeman-Hopfinger scale. I'll come back on this typical scale, but after. So there is some proof in the literature that there is some wave into turbulent flow. For example, this is a typical result of Andrea Maffioli. You can show that the frequency omega and theta omega. Excuse me. You can show the energy as a function of frequency omega and theta omega extract from the flow from the DNS. And for the dotted line is a theoretical dispersion relation, and the other point is the point of the energy of the DNS in the flow. So that comes from the DNS. As you can see, the energy is concentrated around the dispersion relation. This is occur in stratified turbulence. In rotating turbulence, there is some result from experiments from experiment from Yaro and Sharon. This is again the energy that vary with omega and theta. Now the dispersion relation is different, and the energy is concentrated around the dispersion relation. So there is some evidence that the wave exists in this flow, in rotating or in stratified turbulent flow, but there is also some ADs and large structure, and they mix together. So we have an interaction between wave ADs and large scale, as you can show, and it becomes difficult to extract the interaction between all of this structure. Classically, what's happened in the literature, in fact, there is some separate in the literature. There is only studies on separate interaction. For example, we have some people studies only the wave AD interaction. For example, from the article of Moulin and Flore, they study how the wave is deviated by a big ADs. There is some wave-wave interaction, and it is called the wave turbulence, the classical wave turbulence. It is studies. This means that only in the flow you have only wave that occur in the flow, and there is only weak interaction, and you can do some statistics and you can obtain some results. This is developed, for example, by Elvov and al. You can have some wave-wave interaction that transform this wave into ADs, and it's, for example, the wave breaking. And at the end, you can have some interaction, but with wave and large structure. All this classical publication is deal only with separate interaction, but in the turbulent flow, everything is mixed. So one of the question is, can we obtain a global overview of all the interaction in the flow? This is the main goal of this topic. And after, when we have all the the way to obtain all the interaction is to have a good method to separate the wave ADs and large structure. But we know that in stratified turbulence we have some techniques, but it's very limited. I show you again after why it is limited. It is there is some problem with this technique, and in rotating turbulence there is no explicit techniques that extract wave ADs or large structure together. If we can obtain this all the interaction, we can now answer to some question. For example, what is the role played by waves, ADs, and large structure in the transfer of energy from large scale to the dissipation, the smallest scale? Is the mixing is due to wave part or ED part? What is the most powerful structure that mix the flow? It is important in particular in stratified flow. What is the supply process of the large scale? Okay, and is it a self-interaction or an interaction with wave or with ADs? And finally, what is the typical scale of interaction? This is the answer. This is the question, and we answer to this question for this topic. But you can have now a lot of question, and you can use these techniques to answer to your question. So, what is our separation technique? So we start from the Navier-Stokes equation with Boussinesq approximation in rotating frame. So here you have the stationary term for the velocity u and the buoyancy field, the density field, if you want, the variation of the density. We have the classical Navier-Stokes equation with incompressibility, okay, at the last equation. We have the nonlinear term here. We have the Coriolis force here, and we have the gravity here in the middle. We write this equation as follow, just symbolically, just because it's easy to manipulate this. We have a linear equation. Donc, partial derivative of t minus L, it's an operator, the linear operator over for x is equal to non-linear operator, okay, like this. And you add the forcing. The forcing occur in u and b, and x is ux, uy, uz, b, and the pressure. So we have this symbolical equation, and we deal with this. So first, if we want to obtain the dispersion relation, we just remove all the term, remove all the nonlinear term and the forcing term. Okay, we have only the linear system. We can just take the Fourier transform in space and in time. So we have here this problem. This problem is just an eigenvalue problem. And for example, we can solve this problem first, but we have another properties. If we x is non-null if the determinant of this operator is null. So if this determinant is null, you find the dispersion relation omega r is equal to n cos theta, and omega r is equal to 2 omega. Omega is rotation rate sinus theta. So you can find the dispersion relation. It's very easy. If we want to produce some wave, it's very easy. We just put a forcing into the second member of the green function, the linear system. It's just you just inject some Dirac forcing. As you can see, we just put one Dirac and we produce some wave packet and internal gravity wave. Excuse me. So we have this flow. We now compute the energy that occur in this flow. The velocity u is used in the Fourier space. Excuse me. So what we do is just we do a summation of u for each angle theta. Okay, we do a summation of energy for each theta at k down, the wave number, the length scale. After we just do a summation over all the key, and we have the energy for each theta and omega, the energy of the flow for each theta and omega. So this treatment is very easy. It's just a post-treatment of your data. You just do a Fourier transform of your velocity, and after you just compute the energy of each mode, but over a cone of angle theta. If we do this from this animation, we have this dispersion relation. The energy is concentrated around the dispersion relation. Okay, so we can recover the dispersion relation. But what's happened now if you have some large structure that transform your wave? Because the wave is sweeping by this large scale, this large scale, and so the dispersion relation is modified. So you cannot characterize the wave only by the sample dispersion relation. You must take into account the advection, the sweeping effect by the large structure. In a rotating flow, there is, as I say at the beginning of the seminar, there is the geostrophic mode. The geostrophic mode is characterized. We characterize the geostrophic mode by taking the velocity field, but with kz equal to 0. This means that there is no variation along the z-axis. And you, for example, this is a typical kinematic of energy of the GM. Typically, you have no variation along the z-axis. You have only the column. So if we just filter the velocity by taking kz equal to 0, we have the geostrophic mode. This is done in experiment or in simulation. We have the formation. We understand now how the geostrophic mode born into the flow. For the vertical, for the stratified flow, we have, as I said, the shear mode. The shear mode is it's a mode that a shear flow that vary now along the z-axis, but it is constant in the horizontal plane. So this is a typical kinetic energy of the vertical shear horizontal flow, the shear mode. We just take kh equal to 0, so this means that the velocity c vary only in the z-axis. This is done in simulation. This is obtained in simulation, and experiment. It is not easy to obtain the shear mode, because the shear mode is a mode that goes at right and at left. And classically in experiments, you have some boundaries, and it deform your shear mode. But recently, just maybe 6 months, Mordon and Augier in Grenoble, in France, obtain the shear mode. The problem in the experiment is that the shear mode it's a big structure, so you need to have a large measure of your flow, and it is difficult from experimental point of view. But they obtain this shear mode. So, as I say just before, the large structure deform your flow. So how to obtain the characteristic of your wave due to the advection of your by the large structure? We add to the green function, to the linear system, we had the convective term. The convective term is just C gradient of U, or C gradient of B if you have and you can add the C gradient of B if you have the buoyancy. And C is either the GM mode, the geostrophic mode, or the shear mode. So you add to this green function, and now your green function is inhomogeneous because C vary in space and in time. So you must if you want to have all the information of your linear system, you must to inject not one Dirac, but some random Dirac in space and in time. This is what we do. We, for example, just take a random Dirac is like this. I don't know if you can show the animation. You have some Dirac here, for example, some Dirac here, some Dirac everywhere, and each each Dirac produces some wave, and each wave is transformed and deformed and submitted to a deformation of the flow due to the shear, like this at the right or at the left. So you have some a superposition of wave, but each wave is advected, is sweeping by the shear mode. So classically, if we just plot the energy of your flow in function of theta and omega, the red dotted line is the line, the dispersion relation, the classical dispersion relation. But if you just do an assumption that C is homogeneous, you can form, okay, you can have two curves where the energy is concentrated. These two curves, okay, excuse me, is obtained here. You have the classical dispersion relation, but you need to add the Doppler effect due to the advection of your wave, C multiplied by K, and this is the two yellow curve is exactly what we have obtained by just take C equal to constant in time. Excuse me. Now this relation is not it's an exact relation when C is homogeneous, but when C is inhomogeneous, this relation is not valid. In fact, we must to change. We must to find a new dispersion relation. And when C is inhomogeneous, it is difficult to obtain an analytical dispersion relation. So we have define now we have find an implicit definition of wave. So let's start with the homogeneous system. In your homogeneous system, even if you add the convective term, C is equal constant in time and in space, you can solve this equation analytically by your hand. It's just an analytical harmonic oscillator. And for example, for the density, it's very easy to solve the equation. You can find two poles, omega equal omega r and C of ck. Omega r is the classical dispersion relation for the internal gravity wave. And so we have two poles because it varies with omega. There is two poles. One is that is obtained when omega is equal to minus or plus minus omega r minus the Doppler effect, in fact. When your system is inhomogeneous, so you need to add some random Dirac. And now we don't know exactly, we don't have the analytical solution. So we use the simulation of the green function to obtain the same information as in the homogeneous case. So we simulate the green function by taking C equal to the shear mode or to the geostrophic mode, and we detect only the peak in the Fourier space in terms of K and omega. Here we have the peak for omega equal to this dispersion relation. Now we just detect a peak for like this for each simulation, and now this peak define an implicit dispersion relation, and we can now define what is a wave and what is not a wave. So in practice, what we do is first we have a numerical simulation like this. We have the first DNS. From the output, we just take the Fourier transform in space. So we have the F key and T. We extract the large scale, the shear mode or the geostrophic mode. Then we perform a second DNS, the green function DNS, and we advect. We have some random Dirac in time and in space, and we advect by the shear flow extract from the first DNS. At the end, we have some field, the linear field for the linear system, and we perform the last Fourier transform in time. So we have chi and omega. So at the end, we perform the 4-dimensional Fourier transform. One 3-dimensional for the space and 1 dimension for the time. And after, we just detect the peak in the field. Where you have a peak, you have a wave. So the filter zeta is equal to 1. And when you have no peak, zeta equal to 0. And we call this AD domain. We call this AD because it is not a wave. So when we use now this filter to extract the wave part and the AD part, what we perform is just we apply the filter to our velocity field from our DNS. So we perform the Fourier transform in time of the output of our DNS. So we are in the 4-dimensional space T omega, K omega, and after we apply the filter. When zeta is equal to 1, we have the wave, and when zeta equals 0, we have the AT part. So we separate the flow between wave part and eddy part. So this is what we do, but it is expensive to do that. For example, for a modest simulation in a 12 point to the power 3, so it's not high resolution, but the cost is huge, in fact, because you need 1,000 field to be stored. So at the end, the data storage is 12 terabytes, just to thread the problem, to apply our treatment. The second point is that you need to perform the green function, the simulation of the green function. So the cost is not is expensive in terms of data storage and in terms of computation. You need to perform this second DNS. So the problem now, okay, we define zeta, we know how to apply this to velocity field, but it's not exact. We must to understand what's happened when you apply the filter zeta on the component of the velocity. So in stratified case, and I wrote that in case or in isotropic case, in fact, the condition of incompressibility is transformed in Fourier space by the fact that the wave vector is perpendicular to the velocity. Here, this is the wave vector, and so this means that the velocity is perpendicular to k. You can use a spherical coordinate with toroidal and poloidal. This is the two components of your velocity, and this means that since the velocity u is perpendicular to k, there is only two components, toroidal and poloidal, for the velocity. The buoyancy is parallel to z here. So from the Rayleigh theory says that when the Reynolds number is less than 1, I come back at the end, at the second part of the buoyancy Reynolds number, the definition of the buoyancy Reynolds number, but for the moment is not useful. Just when the Reynolds number is less than 1 and the full number is less than 1, okay, you can apply the Rayleigh theory. What's he said? He said that the linear system, the linear equation of the stratified fluid is the linear solution is just obtained by taking only the poloidal and the buoyancy, because toroidal part is purely horizontal, and whereas the buoyancy is in the vertical axis, and only the component of the poloidal part of the velocity has a vertical component. So it's logic. Okay, wave is only poloidal part and buoyancy part. In rotating case, there is no technique because the two component is used. We can show that we have the linear system, and UP and UT are the linear system of your are the solution of your linear system. So there is no separation technique for this. Now, how can we do the filter of the component? First, the wave part. For the wave part, in the stratified case, we just apply the function zeta only on the poloidal part and only on the buoyancy field. So this means that not all the poloidal parts are wave, but only the fraction defined by zeta. For the rotating case, it is the same. This is the global velocity, UT and UP, and we just apply the function zeta into the total velocity. So just a small part of the velocity in rotating case is a wave. The AD part, the AD is defined by the fact that it is not a wave. So we just take the complementary filter. So this means that the toroidal part, the total toroidal part, it is taken into account, and the complementary filter is applied to the poloidal part, and the same for the buoyancy. It is the same trick for the rotating case, and we apply the complementary part. At the end, we come back to the physical space in time and in space. Okay, we are here in k omega, so in 4-dimensional space. We come back to the physical space, and we form the energy from ADs defined here, energy from wave defined here, and energy from large structure, the shear mode, that we can obtain firstly. We do the same trick for the rotating case. We have energy for ADs, wave, and from the geostrophic mode, the mode at kz equal to 0, and the shear mode is the mode at horizontal wave number equal to 0. Note that by using this decomposition, we have in fact a scalar product. So this means that you can project all your velocity onto the wave part, AD part, or large structure part, and you can form an orthogonal, and you have an orthogonal property. So it's a powerful mathematical trick for your decomposition. We use this after in stratified and rotating turbulence. If you compare the difference between the classical Rayleigh decomposition and our decomposition, okay, Rayleigh decomposition it's a pure spatial decomposition. The spatial decomposition, all the poloidal part of the velocity is the wave, and all the buoyancy is the wave. Only in the AD is a pure 2D horizontal velocity, like this. Excuse me, like this. This means that all the when an AD do an overturn of the density in the vertical plane, we don't take it into account because it is when you have an overturn from this Rayleigh from this decomposition, this overturning is taken into account into the wave parts. Whereas in our decomposition, it's a spatial temporal decomposition. The poloidal velocity, just a small part of the poloidal velocity is taken into account into the wave part, and again, it is the same for the buoyancy. And now we have for the AD part, we have the 3D velocity, because okay, we have the 2D part of the ADs, the toroidal part, but now we have a small part of the poloidal and a small part of the buoyancy. So now the overturning of the density can be taken into account, can be done into the eddy part and not into the wave part as the classical Rayleigh decomposition.
Alexandre, I have a question.
Yeah.
So how do you apply this filter? I didn't understand zeta, k, omega. How do you do it in? Yeah. So
Yeah.
this filter, how do you implement it?
Yeah. It's okay. You have a big array, an array. No, 1 minute. You have, for example, an array for kx, ky, kz, and omega. So it is a four-dimensional array. And now you have zeta. Zeta is the same. It's a four-dimensional array. You just have the multiplication
I see.
of the velocity with zeta.
So zeta, you have one somewhere and zero everywhere.
Yes, exactly. It's because the powerful of the Fourier space is that a wave that occur globally in space is just 1 point in the k omega space.
I see. Okay.
It's this is the key of the method. Yes, the key of the method.
I see. Okay. Thank you.
Okay. Now we can apply this decomposition to some physical phenomena, in particular in stratified turbulence. And first, we can ask two questions. We can answer to the question: how waves and eddies interact with one another. So the first question, and the other question is due to the mixing. The mixing occurs in stratified turbulence because the buoyancy, there is some overturning of the buoyancy, and this buoyancy dissipates, and so it creates a mix of the buoyancy in the flow. So we can know, we want to know what is the wave or the proportion of the wave or the eddies that mix the flow. It is not possible to answer to this question in stratified flow because, again, with the Rayleigh decomposition, all the buoyancy is taken into account in the is a wave is take is on all the buoyancy is the wave part. So, for example, here we have a result of our simulation. The black line is ISO density of the flow. So we can now have an animation of our decomposition. At right is the total density, total buoyancy field. In the middle, we have the wave part. And at the right, this is the AD part. Okay, so what we obtain is that we have a lot of wave in the wave part. In fact, there is a few overturning of the isodensity. The black line, the isodensity, is more or less continuous. And this is not the case for the eddy part. There is a lot of overturning. There is a lot of small structure that occur in the flow with overturning. And this is a new feature, in fact, new extraction. In fact, it is difficult because classically, if you just take the poloidal part and the toroidal part, you have some information, but for the density, it is not possible to have this decomposition because, again, the Rayleigh decomposition take all the buoyancy as a wave part. So we perform the numerical simulation with by using a forcing. The forcing is not injected into the shear mode. We take care that the forcing is not injected into the shear mode. We add a viscosity only for the shear mode because you maybe when you perform a stratified turbulence with a forcing, classically you have the shear mode that increase with the time, and it is difficult to saturate the shear mode. Classically, your DNS explodes. So we add some friction term here, alpha, and it is choice to be equal to 1, and this is mean that only a few parts of the total energy is concentrate on the shear mode. Classically, the shear mode is 50% of your flow, and here we reduce the shear mode to 1%. Excuse me, to 1% of your flow. So this is means that your the shear mode still in your flow, but is reduced. And we concentrate our simulation in the transition between two regimes. This is to define the regime, we need the full number. The full number is just the flow inertia over the gravity force, and we use the definition by using epsilon, so it is independent of a typical length scale. And we use the buoyancy Reynolds number. The buoyancy Reynolds number, you can interpret this by the ratio between the Kolmogorov scale over the Osmedov scale. So again, the Osmedov scale is the scale where until where the gravity waves occur. So you have the formula for the Kolmogorov scale and Osmedov scale. When the Reynolds buoyancy is great, is more than 1, this means that okay, we have a large scale where the internal gravity waves dominate the flow, and we have a classical inertial subrange after the Osmedov scale. And when the Reynolds buoyancy number is less than one, this means that all the scale are dominated by internal gravity waves. Some typical value in the atmosphere. Okay, you can in ocean, classically in ocean, the Reynolds buoyancy number is 10 to the power 2. For us, it is difficult for the DNS. It is difficult to have a slow through number, a low through number, and high Reynolds buoyancy number. In the parameter map that is plot here, we have had the result from Andrea, the blue triangle, and the purple triangle is another result from Garanayek. Okay, the circle is our result from the DNS from 50 to the power 3 point and 256 to the power 3 point. We separate the parameter space into two regimes. The first regime is the viscous affected stratified flow, according to the definition of Breton-Hoover. And when the Reynolds number is more than 1, you have in the the strongly stratified turbulence. So this means that okay, the Reynolds number is very low, and you have a high Reynolds number, buoyancy Reynolds number. So what we have done is we have performed the 1-point statistics. Classically, when you are in the homogeneous isotropic turbulence, the classical 1-point statistics, the transfer of energy, is stationary. So this means that the dissipation epsilon is equal to the production P, and you have a compensation between the two, and so your flow is statistically stationary. So we can just use the same way to obtain energy budget, but we use now our scalar product. By using our scalar product, we can have an energy budget for the stratified flow for each part, for the wave part and for the AD part. And usually we can have the shear mode part, but as I say to you, for our simulation, with the level of the shear mode is very low, and so when we compute the equation for the shear mode, it is negligible in comparison with the two other parts, for the wave part and the AD part. Into the wave part, we have the classical dissipation. Okay, here the total dissipation is the kinematic dissipation for the wave plus the dissipation for the buoyancy. This is this part, and we have the injected power. The injected power is just your forcing multiplied by the velocity for the wave. This is the same for the AD. Huh? We use the same trick, and as you can see, compared to the heat, to the energy budget in the isotropic case, we have now some net transfer, here between the two equations for the wave and the AD. The transfer term is just the summation of the nonlinear term for velocity and buoyancy. We call this transfer because it's easy to demonstrate that if we call the transfer term TEGL, we can show that for TEGL is equal to minus TELG. It's just, you can show easily this by applying a triadic summation. And for some term, because as you know, in the energy budget of heat, you have the transfer term, and this transfer term is equal to 0 for the isotropic turbulence. It is the case for the stratified flow. You must to add some other term, and the other term is equal to 0, in fact, and we call this the cascade term. And there is several cascade terms. Again, we use our scalar product and due to our decomposition. So now we can have an overview of the exchange between the wave part and the AD part. The equation like this is not easy. Okay, as we know that this term TWE and W is the opposite of TWW and E, and it is the same for TEEW. It is the opposite of TEW and E. This is the opposition. This is the exchange term. You can represent all this equation by a diagram. It is called a Sankey diagram. It's classical in machinery. In fact, it's like a hydraulic line. You have the injected power P at the beginning of your line, the large scale, in fact, and you have the dissipation at the small scale here. The power P is divided into two parts: power injected into the wave and power injected into the AD. And as you can see, there is more power for this case. There is more power injected into the wave than AD, but at the end, there is a lot of energy that is dissipated by ADs in comparison to the wave. And what's happened? It's happened that there is a lot of exchange of energy from the wave part to the AD part. And the two terms here are not negligible. There is, in fact, an exchange between wave and ADs. So we can now, since we have a global overview of our problem, we can now just plot all the data, the power, the dissipation for the two parts, and since they are opposite, we can plot the transfer term. When the Reynolds buoyancy is more than 1, is very high, like this and like this. In blue, we can show that the dissipation equal to the injected power, whereas in red the injected power into the wave is equal to the dissipation of the wave. So this is mean, and the transfer term is equal to 0. So this is mean that in the case of high Reynolds buoyancy number, there is no net transfer between wave and AD. There is a decoupling dynamics between the two parts. And for Reynolds number less than 1, now we have a transfer, we have a transfer between the wave part and AD part. The power injected into the wave is more than the AD, but we have a coupling. In particular, when the Reynolds number is equal to 1, it's a particular point here. There is an equilibrium, in fact, between dissipation and stratification. And here, or close here, you have a maximum of transfer between the two parts. And now each part are highly coupling, in fact. Okay, so this is means that, okay, from your first question, we have an answer. We can describe the dynamics between the wave part and eddy part. For the second question about the mixing, classically in climate or in weather model, it is used an diffusivity for the buoyancy flux. The buoyancy flux is just the vertical flux of the buoyancy, and n is the Buoyant bicellular frequency. It is linked to the mean gradient of your flow, and you have an approximation that gives that makes that, okay, the buoyancy flux is equal to the mean gradient with the kappa constant here. If we have a balance of energy between available energy, available potential energy, the buoyancy flux is equal to the dissipation of the buoyancy. This is the second point. Again, classically, in a weather model or in a climate model, it is easy to obtain N, the mean gradient, but it is not easy to obtain the buoyancy, and it is not easy to obtain the dissipation. So the kappa is not easy, but we can have this relation. Kappa is the viscosity multiplied by gamma. Gamma is the mixing coefficient multiplied by Reynolds number. If you do this, you can have an approximation of gamma. You can obtain gamma, and you can now inject this gamma into your model, and you can close your model. If we use the decomposition of epsilon into wave part and eddy part, and the same for velocity into eddy part and wave part, then you can decompose your mixing coefficient into the wave part and eddy part. It's just the buoyancy part, wave part L divided by the total kinetic dissipation. So what we do here, we plot the gamma, the coefficient gamma, as a function of Froude number. Again, we add the value of Andrea Maffioli and Naek, and we add the maximum value in the case of pure wave, in interaction with wave, that is obtained by Laurent. The maximum is obtained for gamma equal 1. And as you can show, when the Froude number decrease, or the buoyancy Reynolds number decrease, they are linked together. This means that the gamma E, so the gamma for the ADs decrease, and the gamma wave is close to the total gamma. So this means that there is a lot of mixing due to the wave, exactly as we expect by decreasing the Froude number and the buoyancy Reynolds number. When we increase the buoyancy Reynolds number, or when we increase the Froude number, as you can show, now the gamma obtained by the ADs increase are close to the gamma total, whereas the gamma wave decrease and saturate. in fact, we obtain the gamma E equal more or less 3 gamma W. And if we just check what's happened for the different term of the dissipation for buoyancy and for velocity, velocity here for the wave eddy part and for the wave part, you can show that the dissipation of the wave part for the buoyancy and the dissipation of the wave part of the velocity are more or less equal. The red line are more or less the same. So this is a typical signature of a wave, because for a wave, if the Prandtl number is equal to 1, you dissipate you have an exchange between velocity and buoyancy, and so this means that the two fields dissipate the same amount of energy. Okay, so this is the second result about the mixing, and now we know how this mixing is divided into the wave part and eddy part. This is the last part of my topic. Is about now what is the interaction of wave and eddy and geostrophic mode in rotating turbulence. So again, we have the kinetic energy for the geostrophic mode, and one of the questions is what is the supply process of the geostrophic mode? How the geostrophic mode emerge from the flow? Classically, we have the Greenspan theorem from 1969. He says that this theorem says that there is no resonant triad instability for the geostrophic mode. So it's a sad story, because this means that, okay, classically for the triadic interaction you have this relation, and this relation is forbidden for this relation give nothing in terms of instability. So this means that the geostrophic mode is not to obtain the geostrophic mode is not easy as we expect. So different scenario become with the time, in particular with the Smith and Walef article, and Newell at the beginning. But the Smith and Walef say that maybe there is a quartic instability. This means that there is not a triadic, but 5 wave, that exactly 4 wave, and one geostrophic mode, and there is some interaction between all the wave, and it produces some it gives some energy to the geostrophic mode. So it was demonstrated that this scenario, this instability can occur in experiment. It is done by Brunet et al. You can bypass the Greenspan theorem by another instability, is the near resonant instability. It means that this relation, the triadic relation for the frequency, is not exactly checked. It's more or less equal to 0. In fact, it is equal to an epsilon, with epsilon very small. When you do this, you can obtain numerically and analytically, you can obtain that the GM is fed by this near resonant instability. So this means that we have all the ingredients that feed the GM, but only at the beginning of only at the beginning only in the laminar system. And, when you are in rotating turbulence, is different, because there is a lot of structure, and you have several phenomena. In particular, you have direct and inverse cascade that is injected to the GM. It's just an observation, and this means that the GM is a condensate. In fact, it grows with the time, and it becomes bigger and bigger. It is known that the GM depends on the elongation of the domain. The more the domain is high in comparison with the horizontal section, the more the difficulty, the more excuse me, when the elongation of the domain is high, the GM is more and more it's difficult to emerge from the flow. But what we need is that the GM need, in fact, some 3D fast mode. The 3D fast mode is just a combination of wave and AD, but in fact, the fast mode is something else than the GM in the definition of Buzzi-Coty and all. And it is a non-trivial role for the inverse cascade. This is the same. There is a non-trivial role for the small scale. It is known that for horizontal part of GM, there is an interaction to obtain this horizontal part of GM. You need an interaction between the small scale GM and 3D fast mode. Again, the fast mode is a combination between wave and AD. So since we know that the fast mode is wave and AD, we know that one of the question is what interaction transfers the energy to the GM, in fact. Is it wave-wave, wave-AD, AD-AD, etc., or a self-interaction? And can we obtain a typical scale of this interaction? So again, this is an animation. You can show that this is the flow with some wave. The large structure are the large AD are the GM because it is an horizontal cut. So this is the shadow of the GM, and here the shadow of the GM produce some small wave, whereas here the shadow of the GM produce some ADs and overturning. So it seems that our decomposition is have a behavior as expected. We can decompose the wave part and the AD part of the flow just based on the visualization. We perform again the same another simulation. Maintenant, the GM is very important. Is between 10 and 20% of the total of energy, the large structure. We introduce the inertial Reynolds number is the same as the buoyancy Reynolds number. First, we can demonstrate. I accelerate because maybe it's the time for you. Okay.
We start losing the audience. Maybe how much time will it take, Alexandre?
Maybe 5 minutes. In 5 minutes, it's
sure.
okay.
Five is fine.
Yeah, I have 2 points. First point, I demonstrate. Okay, the GM is it is a 3D. Classically, the GM is only take into account the 2D part, but in fact, the GM is a 3D field. And come back to our global overview. We can apply again the one point statistics, and we can apply how the energy or the global energy of your flow involved in our system. We just inject our decomposition in the Navier-Stokes equation, in the Lynn equation, etc., etc., and we can have this equation. This equation is more complex than in stratified turbulence because we have had now the large structure and the GM mode. So we have a lot of interaction, and now this equation is you cannot interpret this easily. In fact, we need some diagram to help us to interpret this. First at all, we have 3 dissipation for wave AD and GM, 2 injection of energy for wave and AD, and all these terms are the coupling term. Again, when you have TEGL, this means that you have a transfer of energy to the L part from G. So we have energy that is transferred from G to L, helped by the E part. When you have this equation, you can again do a Sankey diagram. P is now it's at the left and dissipation at the right. We have in fact add the unstationary term because this unstationary term is weak, but it's non-negligible in this case, in particular for the rotating case. So we have add this unstationary term. The white boxes is just it's just a box that differentiates the left part and the right part. The left part, this is mean that is an injection of energy. The left part, excuse me, the right part is the left part is an injection of energy. The right part is goes something else from the dissipation or other part. And now you have the all the different all the term here are represented by this connection with the other part. First at all, we can show that for our simulation we inject more energy in the wave part, and there is the energy from the wave part equal to the energy of the dissipation. This is done for each Rossby number, and this means that in fact since dissipation and epsilon are more or less the same, maybe it's superior or inferior, this means that you need a transfer between wave and ADs and GM. You need this transfer. This is the most important thing. The second point is that we have a transfer from a wave to AD like this, and helped by two things. From the ADs, and the second is from the wave. It depends on the Rossby number. And finally, we can have the classical we can have a transfer from wave to the geostrophic mode, either due to the wave and helped by the wave. It's a classical it's exactly what we have in the literature. It's a wave turbulence. In fact, we have waves that produce geostrophic mode, but we know we have another term here. It is helped by the AD term, and this is a new mechanism to transfer the energy from wave to geostrophic mode. We can have another transfer from AD to geostrophic mode, and this is totally new because there is no scenario to transfer the energy from ADs to geostrophic mode, and it is helped by wave and helped by ADs, in fact. Okay, so to summarize it, we have net transfers from wave to ADs, and it is helped by ADs and wave. It's relatively new. But the new part of our result is about the net transfer from wave to GM, either by the wave, okay, it's like in literature, but either by ADs, and it is totally new. And there is some transfer from ADs to GM. Again, it's totally new due to by the wave and by AD. We can go further in the scale analysis, but it takes a time. But what we obtain is that the wave-wave interaction is the main interaction in our flow, but we have an AD wave interaction, and it gives some energy to the GM at large scale. In fact, we can have energy that is give from AD to the GM, and again, it is at large scale. At the end, we recover the classical self-interaction, but the self-interaction of GM with GM that give energy to GM. It is a direct cascade for the 3D case, but for the 2D case, it is an inverse cascade. At the end, we measure that this self-interaction is very weak compared to the other interactions that give energy to the GM. So in conclusion, First, we have developed a new technique to separate the flow into the wave part, AD part, and large structure. It uses the FFT4D and implicit definition of the wave. And now we can characterize the most of the statistics, usually, but by taking into account the wave part and AD part. For the stratified flow, we have a global overview of all interaction. In the case where the shear mode is neglected, we can have some large transfer, and we can have the mixing from the wave and from the AD. For the rotating views, it is the same, and we shown that the wave-wave interaction is the main supply process for the GM, but also the AD wave interaction. So for the end, this method is a very versatile method. All interactions are evaluated, but there is no detailed mechanism. There is no fine mechanism of this interaction. We have just a global measure of this interaction, but without any description in terms of instability, etc. But it should be work on other flow with wave, for example, for MHD. In the perspective, we must refine the selection of advecting flow. It's not easy because the large structure in our case is very simple, but maybe it's not simple as we done. And the filter zeta is a filter that is defined only with 0 and 1, and sometimes the wave and for one wave number with one frequency, maybe there is a proportion of wave and proportion of AD that share the same energy. Okay, we can increase what's happened in stratified flow because again we have decreased the effect of the shear mode. We can increase the Reynolds buoyancy number at higher resolution, and we can apply this, for example, for stratified and rotating flow. Okay, sorry for late because I take a long time, but okay, it's finished for me.
Great, thanks, Alexandre. It is very nice. A lot of mathematics and very interesting stuff. Okay, so we can take some questions. Some questions from the audience.
Can I?
Yeah, please, please.
Yes.
Hello, Professor Alexander. This is Raja. It's very nice talk.
Yeah.
Though I couldn't follow the mathematical details, but with my naive understanding, especially for turbulent flows like planetary flows where waves, turbulence, eddies, many kind of things are there. And one would like to get that kind of abstract picture, what it means waves, what it means eddy, how do they interact with each other. It's not that easy to go with standard procedures. So for that purpose, maybe first separating out through Fourier transforms in terms of colloidal components, toroidal components, and again, trying to advect these Green's functions so that one will be in a position to first get this information on waves. Once that wave information is done, then alternative procedure to go with eddies and try to extract these basic abstract structures. Is that correct, or am I mistaken somewhere?
I'm not totally understand, but it seems to be correct. It's yes. First, we have the numerical simulation, and second point, we simulate the green function, and this green function is we inject in fact the advection term from extract from your first DNS.
Correct.
Okay, this is what you understand now?
Correct.
Okay. Yes. This Okay, this it is the L convective term is a term that is extract the velocity is extract from our DNS.
Correct.
And after at the end, yes, we apply the function zeta because zeta detects in the fourth dimensional space in the space k and omega, kx, ky, kz, and omega.
Correct.
It detects what is the peak and what is the wave and non-wave. What is the linear wave and non-linear wave, and
Right.
non-linear and linear wave, in fact. But for the wave turbulence, the definition of the wave turbulence is the fact that okay, we have the wave. The characteristic of the wave is a linear characteristic. Okay, omega. Okay, okay, here. Here, omega r of k, omega r of p, omega r of q. Omega could be as complicated as, for example, our case, so implicit definition, but this is this is a non-linear triadic interaction, but with a linear definition of omega.
I see.
So yes, in the limitation of our method is, I think, is the function zeta. Zeta is just a function defined. It's a true or false function.
Okay, so we can go to the next question. I guess not. So let me ask one question.
Yeah.
For the GM, the KZ is 0, right? So
yeah.
So yes. We have KX and KY.
Yeah.
And the omega will be 0. The frequency will be 0, right?
Yes. Yes.
So structures or eddies have 0 frequency and the waves have non-zero frequency. Is that kind of
no? Yes, no, but yes, yes. In theory, it's defined by. I'll show you. 1 minute. Yes, no, it's at the beginning. Okay, of course.
Yeah. There's a Rayleigh criteria.
Yes, here's here. Yes, okay. It's classically, yes, it's the geostrophic mode don't vary with the time. But in fact, due to the inverse cascade and due to the dynamics, for us, the geostrophic mode vary in time because this column move into the box. But if we just take the definition, if we take a spatial definition of the geostrophic mode, this is means that only kz equal to 0. We have a definition of the GM. So the GM vary with the time. It's not exactly omega equal to 0. In theory, is omega equal to 0, but only in theory.
I see. Okay. So let me share one screen. So if you allow me, we did. I just want to understand. So I'll just share one slide.
Okay.
Okay. So I will just. I think that will clarify me as well as probably some audience. So, and I think which I kind of here. So this is the for just pure rotation. Okay.
Yeah.
And we looked at various Fourier modes, and we had the time series, and we plotted as function of time. This was done by Manohar, one of my PhD student in the past. So 110 is that geostrophic mode, the red one, which doesn't change with time. The Fourier mode, we just beat the time series, and it just doesn't change with time. I think it can move. The movement, I'm not sure how it moves, but this is not a very long time, but 180 over time. It doesn't change, and other modes are changing with time. In fact, periodic time. So this is turbulence. This is around Reynolds number of 1900, based on large scale U and L. So would I call these two modes 110 and 2121? According to your definition, will that? I mean, there will be waves because when I filter it out, so what happens to the filter? When I filter them out, these two ones, the blue and the green, would be waves, and 110 will come out as a AD according to your filter technique, or no?
No, because as you say, KZ equal to 0 for this mode. So
Right,
KZ
right.
equal to 0 is is for the GM.
Oh,
And
so
maybe it move classically. What's in theory is you have a you must distinguish. You remember it's in the Walef article. It distinguish omega equal to 0 and omega almost equal to 0. And maybe okay, for this case, maybe omega is almost equal to 0. Except if you just add some linear solution, you just add some linear solution for this picture.
I see. Okay, so when you apply the filter, so when zeta is 0, that means there is no this wave number is not having any frequency. No, not frequency. What does it mean physically?
Physically, for example, the green line for the green line, okay, the wave vector 1, 2, and 1. Maybe the frequency in time is not the frequency of the wave. Maybe it's just is another frequency. So this frequency disappear from the wave definition. So this part is okay.
So the dispersion relation, there's a frequency, and if that doesn't match, then it is not a wave.
Yes, exactly. The dispersion relation is the definition of the wave. In fact, but the problem is that when you have a large structure, the definition of the dispersion relation is not easy to obtain. You cannot obtain this analytically, in fact.
Yes. So just one more question. 1-to-1 may have a wave part and an AD part, because some part may be wave-like, because some part matches with the omega dispersion relation, but some don't.
Yes. For example, for the 1-to-1, maybe you add two frequency. Okay, you have your signal here. For me, there is one frequency, but if you add two frequency, first frequency is any frequency, and the second frequency is the frequency of the wave.
I see. Great.
So you have two frequency, and our filter distinguish these two frequency. In fact.
Excellent. Great. So I understand it very well now.
Okay.
Good. Thanks a lot. Okay. So good. So some more questions. Of course, it's very late right now, but
yes, for me, it's the beginning of afternoon.
Yes. You probably need lunch though. Great. I think thanks, Alexandre.
Thank you very much.
Very nice talk, and I think it's very useful technique which people should use. Okay, thanks a lot, and I hope we'll discuss further, because I'm interested in this technique.
Okay, nice, of course, as you want.
Great. All right, thanks.
And thank you, Mahendra, and see you soon, maybe.